I would start going through a bit of a use case style. We start from some place and come up with a use case, and then from there we focus on one specific topic, which would be the compression. In the presentation or for the part one, I would focus more on as I said, example use case in the computer vision area. So we are gonna through an introduction, just make sure that we are on the same page, what federated learning protocol we are talking about, and then we delve more into the problems that we have. So in a way, I'm expecting this gives us some idea about if I am developing a solution, when I'm gonna to put this into use, what challenges I'm gonna to have, how we are solving it, and then how federated learning could play a role there, and then what are the challenges with respect to the federated learning itself. Okay. So I'm pretty sure that all the audience are familiar with the federated learning. Just to make sure that we are on the same page, we are referring to this collaboratively training scheme in which we ensure that the data is decentralized and then we are learning models. So in a way, different clients or participants, they are coordinating with a server to obtain a globally trained AI model, which benefits all the participants. Having this in mind, one question would be that, for instance, how we could scale this, and then how it will look basically on the larger scale, let's say cloud providing type of a services. So for instance, the process in this image here fairly describes what happens in a centralized, synchronized type of federated learning, in which clients or devices are making a request in order to get permission for participation, and then once they are getting this session, they start training some on some local data, and then they end up sending their models to the server for some aggregation, which this aggregated model is then redistributed to the devices. So this kind of a process will end up in some model which gets benefit from the insights of the locally trained data. So then this kind of looks kind of fantastic because we don't share any data, we just send some model. So in a way, it also distributes somehow the training into sub-regions or sub areas and devices which are taking care of it. So it has like many use cases. So some of the example use cases, for instance, could be healthcare. In healthcare, we often don't like to share the images of the, let's say, MRI or some medical image taken from the patients, and then we don't want to share any identification that leads into leaking personal data. So in a way, this seems like kind of interesting that we'd be able to locally train an edge hospital, and then we collectively obtain one model that works well for all the hospitals and institutes. So various healthcare services that require training, they could rely on federated learning. And then within the manufacturing, for instance, let's say we are providing a service to paper manufacturer, and then let's say there are multiple manufacturers, and then they want to do quality control. So it's basically we could collectively train on different, data from different manufacturers to give all those manufacturers a better quality of the service. And then if we take into account, for instance, a situation, like um, well, this is still like kind of manufacturing, but let's say take the Netflix, where we could provide recommendation to each user, and now we want to build a better recommender system. So the same could happen within the industries that are creating, let's say, some product, and then they want to give recommendations to the people based on their usage. And yet, we would like to improve the quality of the recommendations overall for any new, let's say, manufacturer joining. And then many times within the manufacturing, we have to improve predictions of the time series, for instance, predicting how market moves, where we have to produce a specific um, type of a product at what time schedule and so on, kind of predicting the market demand. So this could be also used within that kind of application where someone is providing service for different manufacturers. They want to have their own niche area and their local data, but they could collectively contribute to improving some model. So within the AI, AR, VR metaverse, then there are like plenty of applications on the personalization level to more generic type of use cases, which again, this federated learning could really help. And obviously within the smartphones and IoT type of applications, let's say we would like to run a service for detecting a specific type of, let's say, a bird sound, and then maybe some people are having the capability to retrain or basically give their personalized feedback whether the detection of the bird sound has been correct or wrong. And then, you could take that feedback and collectively improve the general model for everybody. And then at last, it could be like, for instance, autonomous driving. So, different vehicles, different manufacturers that are having, different levels of autonomous driving, and all of them, they are trying to improve over time. So obviously, one way of doing it would be that, each vehicle itself be able to slightly learn some of the parameters and then help to improvement of the overall model for all the vehicles, for instance. So many of the use cases that I am talking about could involve some level of computer vision. That could be, let's say, image classification and object detection and classification, semantic segmentation, or face recognition. So in the rest of the talk, what we are planning to do is that we take one example from, let's say, computer vision, and then we try to see how we could build it and deploy it on a device, and then how we apply federated learning and in what capacity we could do it. So to deal with that, I take the example of the semantic segmentation for autonomous driving. And we are all probably familiar, just to make sure we are on the same page. Semantic segmentation is assigning a label or a category to each pixel in the image. So for instance, if I'm giving as input the above image, then I'm getting a pixel label that tells me what is what. For instance, the road is one color, then the area of the vehicles and cars are, let's say, all blue here, and then the trees are green and so on. So when I want to put this on, let's say, a vehicle, there are like some requirements, and some of those could be the following. For instance, the algorithm would fit on device, and here, for instance, it could be some efficient platform. For instance, let's say a Jetson device could be here, and then it could run in real time. Then the other requirement could be that it be able to handle change in input data, and it performs consistently over time. And then the other one could be that this algorithm could improve also over time, because we are going to see that the algorithms may not work perfectly out of the box once we are deploying them into the environment. So I would like to adopt, let's say, some baseline segmentation method. For instance, we take simply the unit architecture, which has been quite familiar and famous in the literature. So we have some convolution layers, we are having an encoder side, and then we have a decoder with some, let's say, residual connections. And we have an input image, and then the output would be the segmentation map that we have. So simply some convolution layers stacked up each other with, with a bottleneck in the middle and then the decoder. So very famous architecture. Let's say I'm training this, and then I take it to the semantic segmentation. So what I would get as I start getting inputting like the video frames is that obviously the segmentation map, but something that would be probably surprising is that for a fairly similar input, I would start getting inconsistent results. So these are like 4 consecutive frames that I have input into some segmentation algorithm, and what I get is that a different label. So it's almost like, it's the same pixel. In many cases, it's, the same kind of a class category, but a different prediction over time. And then we may start wondering why it's going like this. So probably the model is not performing, obviously model is not performing consistently, but well, the model we had was simply let's say a image-based model. So maybe if we put video into play, this should improve slightly better. But our experiment shows that even for the video-based, semantic segmentation, there is still this kind of inconsistencies in the output. So the question for us would be, how could we, solve this consistency problem of the predictions? Obviously taking temporal changes into account, that would be one. And then another one would be adapting the model as we are on the go. So part of the changes could be that, the environment that our model is facing in real world is totally different from the data that we have been exposing it during the training process. So we could adapt the model as we are taking it into use. But then the question could be, how could we adapt efficiently on the device? So obviously, when I start adapting, it means like some probably training would be involved. It means I have to do backpropagation on the device. It's like I take my cell phone out and then I try to train a neural network on my on my cell phone. Obviously, that does not work. So what could we do? There has been like one aspect of the research that we have been doing. So a bit of a prior work that is known as OXADAPT has been, let's say, having 2 neural networks for the sake of simplicity. A mainnet, which is, let's say, a high capacity, difficult to train on a device, or let's say all the mobile phone network, and then some auxiliary networks which has some trainable variables. And then simply we try to do some sort of a adaptation on these AuxNet as we are seeing the new data that is input to the model. So probably one question here would be, what could go wrong in this case? So something that may happen would be that if we train so much over time, then the AuxNet starts representing something totally different than the mainnet. we start having a collapse in the predictions that we are going to have. So trying to address this, we had last year a trainee, Amir, with us, who tried to elevate this basically differentiation or this big deviation between the two models. And then, for instance, we started like doing a momentum adaptation. So the momentum adaptation is simply that the mainnet is now also adapted with the AUXnet. So it gets like somehow exponentially averaged with the parameters of the AUXnet. But then if we do this kind of adaptation, there could be some limitations. Possibly one limitation to this would be that the mainnet and AUXnet, then shall go or have the same architecture. That means if we want to have acceptable performance, then we have to grow the size of these networks. And then that's obviously something that we could not afford on a, let's say, a mobile device. So we are posed then with the question, how could we have them both efficiently on the device trained? So one way would be that, for instance, we have like a small mainnet and AUXnets, and that probably takes us to this type of a combined architecture where I have like, let's say, a mainnet which is fully frozen, and then I have another, let's say, a momentum network or mainnet 2, and then AUXnet, which are like which are having less parameters, and then they are adapted online. One of them is exponentially smoothed, and then they are still in tandem with some frozen, let's say, large neural network. So this kind of getting the both of the two approaches, elevating the side effects of the previous two methods that I showed you. And then interestingly, this is showing these results are showing very nice how nice that this one works. Those red ones are actually the initial architecture, and then those are like the cases of the collapse where actually it is not capable of doing any good prediction anymore. And as you see, this HRNet at the beginning, the two HRNet lines, they're basically the momentum adapt architecture type of a performance level. Okay, there is a question. Does AUXnet architecture the same as mainnet? Or are the weights of the AUXnet into mainnet? So, okay, this is like with regard to, I assume that's with regard to the original AUXAdapt. And then the point here is that for the AUXAdapt, there is no need that the mainnet and AUXnet have the same type of weight architecture. So mainnet could be of any architecture, and AUXnet could be of its own architecture. So as you see, mainnet is frozen. So in no way we retrain the mainnet on the device. But what happens is that the AUXnet is trained by the pseudo labels that are, produced using the mainnet and then, the previous time step AUXnet. So the segmentation map that you are obtaining then is used to retrain the AUXnet as we are moving forward. So, actually there is no fusion of the weights in the AUXAdapt. And then in the momentum adapt, yes, the architectures are the same. And then this is a exponential average smoothing. So what really happens is that we just smooth the weights of the, let's say, previous time step mainnet, and then we add a fraction of the AUXnet weight to it. So in this momentum adapt, then the mainnet and AUXnet, they have to follow the same architecture in order to allow the fusion of the weights from one to the other one. So it's basically exponential averaging that happens over the weights. I hope that this has answered the question that came through. Okay, so if this has answered the question, then maybe I could now move forward. Okay, so what we discussed so far was not on the device. One question would be that how could we deploy the proposed architecture on a device, and how could we still adapt the model on the device and be efficient? So I leave like these questions like to think a little bit, and then I take a detour to model deployment for the device. So once I want to, let's say, put a model on the device, I usually go through these cycles. I optimize the architecture that I have. That means I may do some neural network pruning, removing some of the weights. I may do some I may do some tricks to make them hardware friendly. So it could be that, for instance, someone decides to, apply some parameter reduction approach, maybe a decomposition-based approach on the weights, or for instance, if you're exploiting a hardware that could, if you're using a hardware that could leverage specific sparsification patterns in the weights, I may try to do, some sparsification there. And then eventually, what really would probably help would be that I would like to have my models quantized. So in a way, I either could do a post-training quantization or a quantization aware training on the models that I would like to apply. I would like to deploy on the device. So, yeah. So as I have now made these models kind of friendly to the device, I deploy them. But then remains like the big question that we have, and that's like, how could we improve the model over time? So let's say now I have this semantic segmentation in my vehicle. Let's say I have my mainnet, which is frozen in the, let's say, 8-bit. I may have my, two models which are adapted efficiently with a small number of parameters in a, suitable bit precision of float over a, deployed over a, let's say, for instance, a Jetson device or something similar, then each of my cars that are, navigating and going in the street from here to there, they are exposed to new data, then they start, locally improving over time. And then they adapt their AuxNet and then the mainnet, and they are having a locally updated model. But then the question that comes is that how could we improve the mainnet 1 over time, or the mainnet 2 and AuxNet, globally for all the models. So probably the answer here would be using some sort of federated learning. Of course, in the system, it would not be a straightforward, it would not be a simple, averaging, because, for instance, the mainnet parameters, they're not modified, whereas, the mainnet 2 and then the AuxNet are modified. So probably what I have to do is I'm sending mainnet 2 and AuxNet of each of these, let's say, vehicles to some server, and then obtain some, let's say, global mainnet and mainnet 2 and AuxNet. And in order to retrain that, let's say, mainnet 1, I may have, to do some semi-supervised type of a learning on some data that I have at hand, and then I redeploy this mainnet. But of course, what really happens falls within the region of the federated learning, whereas, I'm sending some models in some process, maybe not as straightforward as a simple averaging happens there in the server, but then I have to do the federated learning. And then here comes like, the complications when we go at a scale. So we could have, a problem with the communication and bandwidths. So as we start, having a lot of devices participating, the amount of the data communicated between the device and then the server would grow exponentially. So for instance, if we take, let's say, the ResNet, and then you have like some limited number of even clients, once you're, sending the ResNet architecture over and over, they could actually get into terabytes of the data that is communicated between the servers and clients, server and clients. Then, we could have the challenge of the heterogeneity of the devices. So, it could be that if we take like the mobile phone case, it could be that I have the same service, but on different data on different devices. So they may perform differently. They may complete the tasks at different time. They may have different, capacities for training the data. Then it comes to privacy and security. We are discussing a lot that, it's federated learning is pretty much safe because we don't share the data. But then research has showed that we could have, some inverse attacks on the model. So actually the models may reveal the data that is used for training the models in this setup. Then the data quality and distribution is also something of importance. For instance, the data heterogeneity is something that really matters here. In many, real-world scenarios, we are dealing with non-IID data that makes the aggregation a bit of a problem. So as if, here it's like also mentioned, aggregation may not be a straightforward. So in the scenario that I told you, it's not possible to do a simple averaging and improve the main net one, which is a frozen network. So I have to go through extra steps and then make sure the model that I have does not collapse and it's still usable. And then the other factor, which is the resource management. So, we discussed a very simple case that's a synchronized, centralized approach. Then managing resources there is pretty much simple. But imagine that now we are going asynchronous. Imagine that now we are not going to be centralized, whereas each client could himself or itself decide what to do and how to do. Okay. So with this, I think I have given you a little bit of a, idea of how or what kind of challenges we are having in utilizing the federated learning. We could shift probably to the second part of the talk, in which my colleague would more talk about methods for reducing and saving the communication bandwidths. Especially, we have been doing quite a lot of standardization within the MPEG. And I think it has been since 2018 that a neural network compression standard has been going on, which also targets the efficiency of the model compression for federated learning scenarios. Okay, so with this, my part is over. If there are no particular question at this time, then I could hand over to my colleague, Humayun.
Okay, thank you. Any question from Hamid?
Yeah, thanks a lot again, Hamid, for this excellent talk. There's one question maybe we could quickly cover. Are there any data at servers, such as in knowledge distillation learning, how we draw and freeze the weights of mainnet?
Yeah, so in order to be able, to learn at the server with this kind of a setup that I showed you, then there should be some data at the server, and then we have also means of exploiting data distillation there. Yeah.
Okay, thanks a lot.
Thank you.
Okay, let me start sharing. And